Mathematical models are fundamental tools employed across a diverse range of disciplines. They serve as simplified representations of real-world phenomena. These models are crucial for understanding, predicting, and controlling complex systems. The core function of a mathematical model is to translate real-world problems into a structured mathematical framework. This framework typically involves equations, formulas, and defined relationships. By doing so, models enable the systematic analysis and manipulation of various systems. Consider their application in fields such as physics, where they describe the motion of celestial bodies. In engineering, models predict structural integrity or fluid dynamics. Economists use them to forecast market trends, while biologists model population growth or disease spread. Each application demonstrates how complex realities are distilled into manageable mathematical expressions. This simplification allows for rigorous study and the derivation of insights that might otherwise be obscured. The power of mathematical modeling lies in its ability to abstract essential features. This abstraction facilitates a deeper comprehension of underlying mechanisms. It provides a quantitative basis for making informed decisions. Ultimately, mathematical models are indispensable for advancing knowledge and solving practical challenges in countless domains. Creating a mathematical model is a systematic process involving several distinct steps. Each step builds upon the previous one, ensuring a robust and relevant model. This structured approach helps in tackling complex problems effectively. The initial step in mathematical modeling is to clearly define the problem at hand. This involves understanding the specific question the model aims to answer. A precise problem definition guides the entire modeling process. Next, it is essential to identify the relevant variables within the system being modeled. These variables represent the quantities or characteristics that influence the problem's outcome. Understanding the system thoroughly is paramount at this stage. This understanding helps determine which factors are most important for the model. Irrelevant variables can complicate the model unnecessarily. Focusing on key elements ensures the model remains tractable and pertinent. Careful selection of variables directly impacts the model's accuracy and utility. This foundational step sets the stage for all subsequent modeling decisions. Without a clear problem and identified variables, the model lacks direction. Once the problem and variables are defined, the next crucial step involves making assumptions. Assumptions are necessary to simplify the real-world problem for mathematical tractability. Real-world systems are often too complex to model in their entirety. These simplifications make the problem mathematically manageable. They allow us to focus on the most critical aspects without getting bogged down by minor details. Assumptions are not arbitrary, they are carefully considered simplifications. The assumptions may directly shape the model's behavior and its predictive capabilities. For instance, assuming unlimited resources in an economic model simplifies calculations. However, it also defines a specific context for the model's applicability. It is vital to recognize that assumptions also define the model's limitations. Understanding these limitations is crucial for interpreting the model's results correctly. Unstated or unexamined assumptions can lead to misleading conclusions. With the problem defined and assumptions in place, the next step is to formulate mathematical equations. This involves translating the relationships between identified variables into mathematical expressions. These expressions form the core of the model. The equations can range significantly in complexity. They might be simple algebraic equations for straightforward relationships. Alternatively, they could involve complex differential equations for dynamic systems. The choice of mathematical tools depends heavily on the nature of the problem. It also depends on the desired level of detail and accuracy. A population growth model, for example, might use differential equations to describe continuous change. This stage requires a strong understanding of mathematical principles relevant to the system. The goal is to capture the essential dynamics and interactions quantitatively. Accurate formulation is critical for the model's predictive power. The final step in the modeling process involves analyzing the formulated equations and validating the model. Analysis often requires solving the equations, which can be done through various methods. These methods include analytical solutions, numerical techniques, or computer simulations. Once solutions or predictions are obtained, they must be compared to real-world data. This comparison is the essence of validation. The model's predictions are tested against observed outcomes or experimental results. Validation occurs when the model's predictions align sufficiently with the observed data. This alignment indicates that the model accurately represents the real-world phenomenon within its defined scope. A validated model instills confidence in its utility. If the predictions do not align, refinement of the model becomes necessary. This refinement might involve adjusting the initial assumptions. It could also mean incorporating new variables that were initially overlooked. Sometimes, using different mathematical techniques or a more sophisticated model structure is required. Mathematical models offer numerous significant benefits across various fields. They provide powerful tools for understanding, predicting, and optimizing complex systems. These advantages make them indispensable in modern science and engineering. One primary benefit is their ability to facilitate a deeper understanding of complex systems. Models achieve this by breaking down intricate systems into manageable components. This decomposition allows for focused study of individual parts and their interactions. By representing a system mathematically, researchers can identify key drivers and relationships. This process often reveals insights that are not immediately apparent from direct observation. It provides a structured framework for conceptualizing complexity. Mathematical models are exceptionally valuable for prediction and forecasting. They enable us to anticipate future behavior of systems based on current conditions and established relationships. This predictive capability is crucial in many domains. For instance, weather models forecast atmospheric conditions, while economic models predict market trends. Epidemiological models forecast disease outbreaks. Accurate predictions allow for proactive planning and mitigation strategies. Models also play a critical role in optimization and decision-making. They allow for the evaluation of different scenarios without real-world experimentation. This virtual testing can save significant time and resources. By simulating various options, decision-makers can identify the best course of action. This is particularly useful in engineering design, resource allocation, and logistical planning. Models provide a quantitative basis for informed choices. Despite their immense utility, mathematical models are not without limitations. It is crucial to understand these constraints to interpret model results accurately and avoid misapplication. Acknowledging limitations is part of responsible modeling. Models are inherently simplifications of reality. They cannot capture every nuance or detail of a complex system. This simplification is necessary for tractability but means they are not perfect replicas of the real world. The accuracy and reliability of any model are heavily dependent on its underlying assumptions. If these assumptions are flawed or inappropriate, the model's predictions will likely be inaccurate. Therefore, critical evaluation of assumptions is paramount. It is essential to understand a model's specific limitations before applying its results. Every model has a domain of applicability beyond which its predictions may become unreliable. Using a model outside its intended scope can lead to erroneous conclusions. Consequently, interpreting model results must always be done with caution. Predictions should be viewed as informed estimates rather than absolute certainties. The degree of confidence in a model's output should reflect its known limitations. The overall accuracy of a mathematical model depends on several factors. These include the quality of the data used to build and validate the model. Poor data can lead to poor predictions, regardless of model sophistication. Furthermore, the validity of the assumptions made during the modeling process is critical. Unrealistic assumptions undermine the model's foundation. Finally, the appropriateness of the mathematical techniques employed also dictates accuracy. Despite these limitations, mathematical models remain indispensable tools across science, engineering, and many other fields. Their ability to provide structure, insight, and predictive power far outweighs their inherent simplifications. They are powerful instruments for understanding and navigating our complex world.